Metals and non-metals. Physical properties. Physical properties. Metals. The easiest way to start grouping substances is by comparing their physical properties. Collect the samples of following metals: iron, copper, aluminium, magnesium, sodium, lead, zinc, and any other metal that is easily available. Iron, copper, aluminium, magnesium, sodium, lead, zinc. Take an aluminium or copper wire. Clamp this wire on a stand as shown in figure. Fix a pin to the free end of the wire using wax. Heat the wire with a spirit lamp near the place where it is clamped. What do you observe after some time? Note your observations. Does the metal wire melt? The above activity shows that metals are good conductors of heat and have high melting points. The best conductors of heat are silver and copper. Lead and mercury are comparatively poor conductors of heat. Do metals also conduct electricity? Let us find out. Set up an electric circuit as shown in figure 3.2. Place the metal to be tested in the circuit between terminals A and B as shown. Does the bulb glow? What does this indicate? You must have seen that the wires that carry current in your homes have a coating of polyvinyl chloride or PVC or a rubber-like material. Why are electric wires coated with such substances? Non-metals. In the previous class you have learned that there are very few non-metals as compared to metals. Some of the examples of non-metals are carbon, sulfur, iodine, oxygen, hydrogen, etc. The non-metals are either solids or gases except bromine, which is a liquid. Carbon, sulfur, iodine, oxygen, hydrogen, bromine. Most non-metals produce acidic oxides when dissolved in water. On the other hand, most metals give rise to basic oxides. You will be learning more about these metal oxides in the next section. Chemical properties of metals. We will learn about the chemical properties of metals in the following sections. For this, collect the samples of following metals: aluminium, copper, iron, lead, magnesium, zinc, and sodium. What happens when metals are burnt in air? You have seen that magnesium burns in air with a dazzling white flame. Do all metals react in the same manner? Almost all metals combine with oxygen to form metal oxides. Metal plus oxygen gives metal oxide. For example, when copper is heated in air, it combines with oxygen to form copper 2 oxide, a black oxide. 2Cu plus O2 gives 2CuO. Similarly, aluminium forms aluminium oxide. 4Al plus 3O2 gives 2Al2O3. Recall from chapter 2 how copper oxide reacts with hydrochloric acid. We have learned that metal oxides are basic in nature. But some metal oxides, such as aluminium oxide, zinc oxide, etc., show both acidic as well as basic behavior. Such metal oxides which react with both acids as well as bases to produce salts and water are known as amphoteric oxides. Aluminium oxide reacts in the following manner with acids and bases. Al2O3 plus 6HCl gives 2AlCl3 plus 3H2O. Al2O3 plus 2NaOH gives 2NaAlO2 plus H2O. Most metal oxides are insoluble in water, but some of these dissolve in water to form alkalis. Sodium oxide and potassium oxide dissolve in water to produce alkalis as follows. Na2O solid plus H2O liquid gives 2NaOH aqueous. K2O solid plus H2O liquid gives 2KOH aqueous. We have observed that all metals do not react with oxygen at the same rate. Different metals show different reactivities towards oxygen. Metals such as potassium and sodium react so vigorously that they catch fire if kept in the open. Hence, to protect them and to prevent accidental fires, they are kept immersed in kerosene oil. At ordinary temperature, the surfaces of metals such as magnesium, aluminium, zinc, lead, etc. are covered with a thin layer of oxide. The protective oxide layer prevents the metal from further oxidation. Iron does not burn on heating, but iron filings burn vigorously when sprinkled in the flame of the burner. Copper does not burn, but the hot metal is coated with a black-colored layer of copper-2 oxide. Silver and gold do not react with oxygen even at high temperatures. After performing, you must have observed that sodium is the most reactive of the samples of metals taken here. The reaction of magnesium is less vigorous, implying that it is not as reactive as sodium. But burning in oxygen does not help us to decide about the reactivity of zinc, iron, copper or lead. Let us see some more reactions to arrive at a conclusion about the order of reactivity of these metals. What happens when metals react with water? Metals react with water and produce a metal oxide and hydrogen gas. Metal oxides that are soluble in water dissolve in it to further form metal hydroxide. But all metals do not react with water. Metal plus water gives metal oxide plus hydrogen. Metal oxide plus water gives metal hydroxide. Metals like potassium and sodium react violently with cold water. In case of sodium and potassium, the reaction is so violent and exothermic that the evolved hydrogen immediately catches fire. 2K solid plus 2H2O liquid gives 2KOH aqueous plus H2 gas plus heat energy. 2Na solid plus 2H2O liquid gives 2NaOH aqueous plus H2 gas plus heat energy. The reaction of calcium with water is less violent. The heat evolved is not sufficient for the hydrogen to catch fire. Ca solid plus 2H2O liquid gives CaOH twice aqueous plus H2 gas. Carbon, sulfur, metals like aluminium, iron and zinc do not react either with cold or hot water, but they react with steam to form the metal oxide and hydrogen. 2Al solid plus 3H2O gas gives Al2O3 solid plus 3H2 gas. 3Fe solid plus 4H2O gas gives Fe3O4 solid plus 4H2 gas. Metals such as lead, copper, silver and gold do not react with water at all. How do metals react with solutions of other metal salts? Reactive metals can displace less reactive metals from their compounds in solution or molten form. How do metals react with solutions of other metal salts? Take a clean wire of copper and an iron nail. Put the copper wire in a solution of iron sulfate and the iron nail in a solution of copper sulfate taken in test tubes. Record your observations after 20 minutes. In which test tube did you find that a reaction has occurred? We have seen in the previous sections that all metals are not equally reactive. We checked the reactivity of various metals with oxygen, water and acids. But all metals do not react with these reagents. So we were not able to put all the metal samples we had collected in decreasing order of their reactivity. Displacement reactions studied in Chapter 1 give better evidence about the reactivity of metals. It is simple and easy if metal A displaces metal B from its solution. It is more reactive than B. Metal A plus salt solution of B gives salt solution of A plus metal B. Which metal, copper or iron, is more reactive according to your observations? The reactivity series. The reactivity series is a list of metals arranged in the order of their decreasing activities. After performing displacement experiments, the following series, known as the reactivity or activity series, has been developed. How do metals and non-metals react? In the above activities, you saw the reactions of metals with a number of reagents. Why do metals react in this manner? Let us recall what we learned about electronic configuration of elements in class 9. We learned that noble gases which have a completely filled valence shell show little chemical activity. We therefore explain the reactivity of elements as a tendency to attain a completely filled valence shell. Let us have a look at the electronic configuration of noble gases and some metals and non-metals. We can see from the table that a sodium atom has one electron in its outermost shell. If it loses the electron from its M shell, then its L shell now becomes the outermost shell, and that has a stable octet. The nucleus of this atom still has 11 protons, but the number of electrons has become 10. So, there is a net positive charge giving us a sodium cation, Na+. On the other hand, chlorine has 7 electrons in its outermost shell, and it requires one more electron to complete its octet. If sodium and chlorine were to react, the electron lost by sodium could be taken up by chlorine. After gaining an electron, the chlorine atom gets a unit negative charge because its nucleus has 17 protons and there are 18 electrons in its K, L and M shells. This gives us a chloride anion C1-. So both these elements can have a give and take relation between them as follows. Na gives Na plus E minus, Cl plus E minus gives Cl minus, Na plus Cl gives Na plus into Cl minus. Sodium and chloride ions, being oppositely charged, attract each other and are held by strong electrostatic forces of attraction to exist as sodium chloride or NaCl. It should be noted that sodium chloride does not exist as molecules but aggregates of oppositely charged ions. Let us see the formation of one more ionic compound, magnesium chloride. The compounds formed in this manner by the transfer of electrons from a metal to a non-metal are known as ionic compounds or electrovalent compounds. Can you name the cation and anion present in MgCl2? Properties of ionic compounds. To learn about the properties of ionic compounds, let us perform the following activity. Take solid sodium chloride on a metal spatula and bring it into the blue flame of the Bunsen burner. We see that it imparts golden yellow color to the flame. Similarly, potassium salts impart violet color and barium salts impart green color to the flame. Take salts in a beaker Set up the electrical circuit as shown. On switching on the current, the bulb is found to glow. This shows that an ionic compound does not conduct electricity in the solid state. Take water in a beaker and dissolve any one of the above salts into it. Set up the electrical circuit as shown. On switching on the current, the bulb is found to glow. This shows that the salt's solution conduct electricity. You may have observed the following general properties for ionic compounds. 1. Physical nature. Ionic compounds are solids and are somewhat hard because of the strong force of attraction between the positive and negative ions. These compounds are generally brittle and break into pieces when pressure is applied. 2. Melting and boiling points. Ionic compounds have high melting and boiling points. This is because a considerable amount of energy is required to break the strong inter-ionic attraction. 3. Solubility. Electrovalent compounds are generally soluble in water and insoluble in solvents such as kerosene, petrol, etc. 4. Conduction of electricity. The conduction of electricity through a solution involves the movement of charged particles. A solution of an ionic compound in water contains ions which move to the opposite electrodes when electricity is passed through the solution. Ionic compounds in the solid state do not conduct electricity because movement of ions in the solid is not possible due to their rigid structure. But ionic compounds conduct electricity in the molten state. This is possible in the molten state since the electrostatic forces of attraction between the oppositely charged ions are overcome due to the heat. Thus, the ions move freely and conduct electricity. Occurrence of metals. The Earth's crust is the major source of metals. Seawater also contains some soluble salts such as sodium chloride, magnesium chloride, etc. The elements or compounds which occur naturally in the Earth's crust are known as minerals. At some places, minerals contain a very high percentage of a particular metal, and the metal can be profitably extracted from it. These minerals are called ores. Extraction of metals. You have learned about the reactivity series of metals. Having this knowledge, you can easily understand how a metal is extracted from its ore. Some metals are found in the Earth's crust in the free state. Some are found in the form of their compounds. The metals at the bottom of the activity series are the least reactive. They are often found in a free state. For example, gold, silver, platinum and copper are found in the free state. Copper and silver are also found in the combined state as their sulfide or oxide ores. The metals at the top of the activity series are so reactive that they are never found in nature as free elements. The metals in the middle of the activity series are moderately reactive. They are found in the Earth's crust mainly as oxides, sulfides or carbonates. You will find that the ores of many metals are oxides. This is because oxygen is a very reactive element and is very abundant on the Earth. Thus, on the basis of reactivity, we can group the metals into the following three categories: metals of low reactivity, metals of medium reactivity, metals of high reactivity. Different techniques are to be used for obtaining the metals falling in each category. Several steps are involved in the extraction of pure metal from ores. A summary of these steps is given in the following figure. Each step is explained in detail in the following sections. Enrichment of ores. ores mined from the earth are usually contaminated with large amounts of impurities such as soil, sand, etc., called gangue. The impurities must be removed from the ore prior to the extraction of the metal. The processes used for removing the gangue from the ore are based on the differences between the physical or chemical properties of the gangue and the ore. Different separation techniques are accordingly employed. Extracting metals low in the activity series. Metals low in the activity series are very unreactive. The oxides of these metals can be reduced to metals by heating alone. For example, cinnabar or HGS is an ore of mercury. When it is heated in air, it is first converted into mercuric oxide or HgO. Mercuric oxide is then reduced to mercury on further heating. 2HgS solid plus 3O2 gas on heating gives 2HgO solid plus 2SO2 gas. 2HgO solid on heating gives 2Hg liquid plus O2 gas. Similarly, copper, which is found as Cu2S in nature, can be obtained from its ore by just heating in air. 2Cu2S plus 3O2 gas on heating gives 2Cu2O solid plus 2SO2 gas. 2Cu2O plus Cu2S on heating gives 6Cu solid plus SO2 gas. Extracting metals in the middle of the activity series. The metals in the middle of the activity series such as iron, zinc, lead, copper, etc. are moderately reactive. These are usually present as sulfides or carbonates in nature. It is easier to obtain a metal from its oxide as compared to its sulfides and carbonates. Therefore, prior to reduction, the metal sulfides and carbonates must be converted into metal oxides. The sulfide ores are converted into oxides by heating strongly in the presence of excess air. This process is known as roasting. The carbonate ores are changed into oxides by heating strongly in limited air. This process is known as calcination. The chemical reaction that takes place during roasting and calcination of zinc ores can be shown as follows. Roasting. 2ZnS solid plus 3O2 gas on heating gives 2ZnO solid plus 2SO2 gas. Calcination. ZnCO3 solid on heating gives ZnO solid plus CO2 gas. The metal oxides are then reduced to the corresponding metals by using suitable reducing agents such as carbon. For example, when zinc oxide is heated with carbon, it is reduced to metallic zinc. ZnO solid plus C solid gives Zn solid plus CO gas. You are already familiar with the process of oxidation and reduction explained in the first chapter. Obtaining metals from their compounds is also a reduction process. Besides using carbon, that is coke, to reduce metal oxides to metals, sometimes displacement reactions can also be used. The highly reactive metals such as sodium, calcium, aluminium, etc. are used as reducing agents because they can displace metals of lower reactivity from their compounds. For example, when manganese dioxide is heated with aluminium powder, the following reaction takes place. 3MnO2 solid plus 4Al solid gives 3Mn liquid plus 2Al2O3 solid plus heat. Can you identify the substances that are getting oxidized and reduced? These displacement reactions are highly exothermic. The amount of heat evolved is so large that the metals are produced in the molten state. In fact, the reaction of iron 3 oxide or Fe2O3 with aluminium is used to join railway tracks or cracked machine parts. This reaction is known as the Thermit reaction. Fe2O3 solid plus 2Al solid gives 2Fe liquid plus Al2O3 solid plus heat. Extracting metals towards the top of the activity series. The metals high up in the reactivity series are very reactive. They cannot be obtained from their compounds by heating with carbon. For example, carbon cannot reduce the oxides of sodium, magnesium, calcium, aluminium, etc. to the respective metals. This is because these metals have more affinity for oxygen than carbon. These metals are obtained by electrolytic reduction. For example, sodium, magnesium and calcium are obtained by the electrolysis of their molten chlorides. The metals are deposited at the cathode, whereas chlorine is liberated at the anode. The reactions are: at cathode, Na plus plus E minus gives Na. At anode, 2Cl minus gives Cl2 plus 2E minus. Similarly, aluminium is obtained by the electrolytic reduction of aluminium oxide. Refining of metals. The metals produced by various reduction processes described above are not very pure. They contain impurities which must be removed to obtain pure metals. The most widely used method for refining impure metals is electrolytic refining. Electrolytic refining. Many metals such as copper, zinc, tin, nickel, silver, gold, etc. are refined electrolytically. In this process, the impure metal is made the anode and a thin strip of pure metal is made the cathode. A solution of the metal salt is used as an electrolyte. The apparatus is set up as shown in figure. Electrolytic refining of copper. The electrolyte is a solution of acidified copper sulfate. The anode is impure copper, whereas the cathode is a strip of pure copper. On passing electric current, pure copper is deposited on the cathode. On passing the current through the electrolyte, the pure metal from the anode dissolves into the electrolyte. An equivalent amount of pure metal from the electrolyte is deposited on the cathode. The soluble impurities go into the solution, whereas the insoluble impurities settle down at the bottom of the anode and are known as anode mud. Corrosion. You have learned the following about corrosion in Chapter 1. Silver articles become black after some time when exposed to air. This is because it reacts with sulfur in the air to form a coating of silver sulfide. Copper reacts with moist carbon dioxide in the air and slowly loses its shiny brown surface and gains a green coat. This green substance is copper carbonate. Iron, when exposed to moist air for a long time, acquires a coating of a brown, flaky substance called rust. Let us find out the conditions under which iron rusts. Take 3 test tubes and place clean iron nails in each of them. Label these test tubes A, B and C. Pour some water in test tube A and cork it. Pour boiled distilled water in test tube B. Add about 1 ml of oil and cork it. The oil will float on water and prevent the air from dissolving in the water. Put some anhydrous calcium chloride in test tube C and cork it. Anhydrous calcium chloride will absorb the moisture, if any, from the air. Leave these test tubes for a few days and then observe. You will observe that iron nails rust in test tube A, but they do not rust in test tubes B and C. In the test tube A, the nails are exposed to both air and water. In the test tube B, the nails are exposed to only water, and the nails in test tube C are exposed to dry air. What does this tell us about the conditions under which iron articles rust? Prevention of corrosion. The rusting of iron can be prevented by painting, oiling, greasing, galvanizing, chrome plating, anodizing or making alloys. Galvanization is a method of protecting steel and iron from rusting by coating them with a thin layer of zinc. The galvanized article is protected against rusting even if the zinc coating is broken. Can you reason this out? Alloying is a very good method of improving the properties of a metal. We can get the desired properties by this method. For example, iron is the most widely used metal, but it is never used in its pure state. This is because pure iron is very soft and stretches easily when hot. But if it is mixed with a small amount of carbon, about 0.05%, it becomes hard and strong. When iron is mixed with nickel and chromium, we get stainless steel, which is hard and does not rust. Thus, if iron is mixed with some other substance, its properties change. In fact, the properties of any metal can be changed if it is mixed with some other substance. The substance added may be a metal or a non-metal. An alloy is a homogeneous mixture of two or more metals, or a metal and a non-metal. It is prepared by first melting the primary metal and then dissolving the other elements in it in definite proportions. It is then cooled to room temperature. If one of the metals is mercury, then the alloy is known as an amalgam. The electrical conductivity and melting point of an alloy is less than that of pure metals. For example, brass, an alloy of copper and zinc, and bronze, an alloy of copper and tin, are not good conductors of electricity, whereas copper is used for making electrical circuits. Solder, an alloy of lead and tin, has a low melting point and is used for welding electrical wires together.